In order for you to truly understand Citrix technologies and to truly become an expert at it, it is inevitable that you master and understand the interworkings of the independent computing architecture, or the ICA protocol, otherwise known as the ICA protocol. Now, the ICA protocol can be, in later terms, be referred to as HDX, or High Definition Experience. That's just simply adding additional plugins to the ICA protocol in order to make it work with applications like 3D rendering and make it work with, higher end stuff. But again, in order for you to become a true expert at Citrix, you have to understand the interworkings of the ICA protocol. And I'm going to go through the basics of what makes this remote protocol such a success, such a hit, and so important from an intellectual capital perspective to Citrix. So for starters, the independent computing architecture protocol is a presentation layer protocol on the OSI model. Now, this is basic networking at this point, right? But it's important to understand this because, well, for starters, this might be a question on the exam. But for other reasons as well, you notice that it is a presentation layer protocol on the OSI model. One of the names that I used to really like for XenApp used to be presentation server, because it made a lot of sense. It's a presentation layer protocol on the OSI model, and as a result, presentation server. So there was a lot of correlation there between the ICA protocol and the name of the actual product. So if you're ever wondering why at some point Citrix chose Citrix presentation server or MetaFrame presentation server, it's because the ICA protocol is a layer on the OSI model at the presentation layer level, essentially. Now, the ICA protocol is also a very thin protocol. This is one of the reasons why it is very popular. It doesn't require a lot of overhead in order to transfer data from the server over to the client side. As a matter of fact, if you break it down in its very basic terms, all you're really transmitting from the server or from the client over to the server, and you're getting back in return a response, is you're transmitting your keyboard and your mouse clicks from the client onto the server. They're being executed on the server side, and then all you're getting in return are screen updates of what's actually going on the server. So you're getting your screen at the client side refreshed with those bits that have actually been modified based on the keyboard commands and the mouse clicks that you've initiated. Now, of course, the independent computing architecture, the ICA protocol, we wish that it was just screenshot updates and keyboard and mouse clicks, right? That would be an ideal world. However, in today's world, we need more peripherals. We need more printer support, more scanner support, more USB support. We need to be able to access files. As a result, when you add all of this functionality on top of the ICA protocol, now you have to understand the inner workings of this protocol in order to tweak it for the most optimized performance possible based on the scenario that you're trying to accomplish. So again, in its most basic form, it's a very thin protocol that is used to kind of refresh your screen based on the keyboard and mouse click that you've initiated. Now, it's also extremely well optimized for the WAN. I've used the ICA protocol back then when we were using modems with 9600 baud rate. I mean, it was built for a time where dial-up was kind of the standard of how you would access these resources over the internet. And back then, latency was very high, slow links, and the ICA protocol performed very well for a lot of applications back then. So it's WAN optimized, it's very latency tolerant, so it can tweak itself and adjust itself based on the latency that it detects on the actual connection link. It also works over standard SSL. So what does that mean to work over standard SSL? So standard SSL will typically use TCP ports. So these would be standard TCP ports, like port 443 for secure SSL connection. So you're not using anything like UDP or any protocol that requires specific equipment or that requires opening very, very specific ports on an actual firewall. So it's able to encapsulate, since the ICA protocol is a TCP based protocol, it's able to use a standard SSL to kind of encrypt that traffic between wherever you're connecting from and that server in order for you to have that secure communication between the two. You can also bandwidth optimize the ICA protocol. That's one of the very powerful things that you can get with it. So you remember earlier on I was talking about, well, if you break it down into its very basic essentials or format, the ICA protocol is a very thin protocol. Again, it's screen updates, keyboard and mouse clicks. But when you start to tap on top of it peripheral support for printers and scanners and USB drivers and others, it starts to become very fat instead of being a very thin protocol. So the bandwidth optimization of the ICA protocol allows you to say, I only want the printer bandwidth to consume, say, 10% of my overall bandwidth. I only want my USB to consume 5%, and I want to give all the rest to screen updates, keyboard, and mouse clicks. In this manner, you're doing a sort of quality of service. You're optimizing the existing bandwidth to make sure that the user experience doesn't suffer, and things like printing don't take up the majority of the bandwidth that's available. This is especially useful in cases where you have very limited bandwidth and you have to make do with what you've got. You would give front-end support to the services that are more user experience sensitive, and then the back end things like printing, they could probably wait a little bit on them, or they might not, just click print and walk up to the printer. So you might be able to buy yourself a little time there and optimize that protocol for a very efficient user experience. Now, things like printing, file transfers, those will reduce performance inevitably. And again, this is why the bandwidth optimization of the ICA protocol is necessary. Because if someone is trying to transfer a PDF or an Excel spreadsheet or maybe a Word document that is a couple of meg over a link that has limited bandwidth, then that's going to inevitably have a performance degradation from a user perspective. So it's important here to understand that the ICA protocol, if you're not tapping on top of it all of the additional peripherals, is very thin, very fast. As soon as you stop to add a lot of these peripherals, at that point you start to need to do bandwidth optimization and prioritization of these packets and these virtual channels in order to maintain that fantastic user experience. Now, which layer of the OSI model is the ICA protocol at again? Come on, I just mentioned it not too long ago. Anyone? Bueller. All right, so those that said presentation layer, you're absolutely correct. Now, this figure here is a representation of a typical OSI model. This is essentially networking 101, networking essentials 101. And what I'm trying to show you here is essentially how the packet flows between the server and the client, and how it kind of gets composed on the server and decomposed on the other side. So since we said that the ICA protocol works at the presentation layer, you'll find that as soon as the client is initiating those mouse clicks and those keyboard clicks, and they're interacting with the application layer is then going to send that to the presentation layer. Presentation layer is going to send it down the stack all the way to the physical layer. The physical layer will then transfer it across, and then it gets deconstructed on the other side all the way up to the presentation layer. Now, why am I showing you this? I'm showing you this because this is a high-level overview of how the packet is going to be transferred from the server essentially all the way over to the client, and how at each layer of the OSI model, different components are added to that packet before it actually hits the physical layer and gets transported. So you might have the session packet that gets added here, you're having the transport layer packet that gets added here. So things are getting tackled on top of it, and they're being transferred all the way to the other side. And at this point, the values in that packet that refer to the physical layer get translated here, the data link layer, the network layer, all the way to the presentation layer. Now, when it gets all the way up to the presentation layer, there's more things that happen here. The ICA protocol is made up of several virtual channels that I'll talk about in a second. Now, it's at this presentation layer that these virtual channels start to get decomposed, and it was very important for me to make you understand that it's at this layer that all that magic is happening before it gets presented back to the application for execution again on the other side. So the ICA packet, let's take a look at the ICA packet, what it's made of, and essentially why it's so different, right? So the ICA packet in its purest format, if you're going to take a look at it here, it eventually gets wrapped into a TCP packet before it gets down and gets transported. That's the transport packet essentially. So the ICA packet is wrapped inside of a TCP packet and gets put on its way on the wire, right? But if you want to break down the ICA packet internally to see what it's made up of, you'll find that these are the things over here and the frame trailer that make up the ICA packet. So you have things like command, you have things like, or let's start down here. So you have the frame header, and we'll talk about what those mean, that get tapped onto the ICA protocol. You have the reliable header, or the reliable packet, that also gets added onto this ICA packet. So all of these get tapped on, including a frame trailer, before it gets encapsulated into the TCP packet. Now you'll notice that I have command and I have a star next to it. Command is the only thing that's constant in the ICA packet. All of the others are optional framing components of the ICA packet, with the exception of command. Command essentially makes up the bulk of the ICA protocol. It makes up those mouse clicks, those keyboard strokes, those screenshot updates. All of that is essential. That's the essential ICA packet. Everything else that you see here are things that get tapped on to the ICA packet to accomplish a certain task, and we'll talk about that. Some of them are pretty self-explanatory, like compression. Well, if you want to compress it more in order for it to go faster across the link, then you add a compression value to it. So this is what makes up the ICA packet in general, that gets wrapped into this TCP packet before it gets set on its way on the network. All right, so let's break it down. So the ICA packet, again, is made up of some optional components and some required components. Command, which is listed here in orange, is the only value within the ICA packet that is constant. It has to be there. It is not optional. So what is a frame head, right? So the frame head is an optional framing protocol header. So this is a prefix. This is one thing that you add as a starter, essentially, for that ICA packet. Then you have the reliable. If you want to add reliability options within the ICA packet for the transmission protocol, then you would add the reliable frame. You have the encryption. If you're trying to encrypt that ICA protocol for higher security, then you can add that as well. Again, that's an optional component. You have compression. If you want it to be compressed, if you're trying to, maybe it is a link that has very limited bandwidth and you want to compress it more than normal, then you would add that compression value to it as well. Command is required. It's the beginning of the base ICA protocol, right? So the base ICA protocol data. So that is the only thing that is constant within that ICA packet. You have the command data. That's also optional. Those are data bytes that are associated with a specific command. And then finally, you have the frame trail, which essentially kind of ends that particular ICA packet. And it's also an optional framing protocol. These are important to know. I don't know if you're going to be quizzed on those on the exam. Those are typically what we studied, what I learned when I was learning Citrix. I don't see those much on the exams these days, but you can see how important it is for you to understand these, to understand the construct of the actual ICA packet, to understand the ICA packet and how it interacts with the TCP packet and how it gets wrapped into it before it gets sent out on the wire. So all of this stuff I'm giving you, you might be quizzed on, you might not, but it's stuff that you should understand. So we talked about the command that is a frame that is constant on the ICA protocol. We also talked about the fact that one of the advantages that the ICA protocol has over different or other remote protocols is the fact that it has these virtual channels. Now, what does it mean to have a virtual channel? All of the things that you see in here are components that get added into a single ICA packet and sent over the wire. Now, why is this important? Well, without virtual channels, what you would have is essentially the printing data that would have to be sent as a separate packet on the wire. The audio data sent as a separate packet on the wire. The drive mappings, separate packet on the wire. Clipboard mappings, etc. All of these would be independent packets that you're sending and flooding that network with. What ICA allows you to do is, instead of sending one packet for each type of data, it allows you to encapsulate all of this data into a single ICA packet and put it on the actual wire and send it once. Now, this is where you can go in and optimize it, right? So in that single ICA packet, you can go in and give priority or not to the printing data or the audio data. Maybe the audio data doesn't need to be here. You could disable it if that particular application doesn't need audio. Thereby, disabling virtual channels will enhance the performance of the ICA protocol. Now, the base, the essence of the ICA protocol, what makes up the heart of the ICA protocol, is known as thin wire 3. right? ThinWire 3, the number 3. Remember when I was talking to you about independent computing architecture version 3.0, ThinWire 3. So ThinWire 3 is essentially the video, keyboard, and mouse. This is the essential of the ICA protocol. That's that command that we talked about that is transporting the basics. That would be it. All of these are also, while they're optional and can be disabled, but those are also essential to the actual ICA protocol. The compression, the reliability, all of the other stuff, that's what's considered optional at that point. Now, the ICA protocol is made up of 32 virtual channels. So inside of each packet, you can have up to 32 of these data points essentially being transported into a single packet, and you can optimize them as well. Now, it's important to know that the RDP virtual channels, the Microsoft Remote Desktop Protocol virtual channels, are very different than those that you see here with the ICA virtual channels. So they're not the same. Do not confuse that. It's important to understand the difference here. So the ICA stack. So I showed you on the OSI model a little earlier how things get transferred between the server and the client, or the client and the server, and how they get decomposed. And I mentioned that when things get to the presentation layer, then in addition to that ICA packet and that TCP packet being decomposed, then that ICA packet also needs to be decomposed. And this gives you a good example here of what I mean by that ICA packet being decomposed. So the ICA stack, when it's being transferred from the client to the server, or back and forth between the server and the client, then there are components of that that need to be decomposed as well. So if you're sending that graphics update, or those graphics screenshot updates, for example, between the server and the client for display, then that is going to get encapsulated with the ICA WinStation driver. It's going to get the protocol drivers. It's going to get the transport driver. It's going to go all the way. It's going to travel that OSI model, etc. Going to get up to the presentation layer again, and it's going to get decomposed there. So the transport driver is going to get off of it, the protocol driver. It's going to go through the ICA WinStation driver, and then it's going to be displayed at the client's graphics monitor, or whatever it is. So in addition to that TCP packet that is being decomposed as it's going through the OSI model, the presentation layer ICA stack also has to get decomposed. Why? Because it is carrying virtual channels. So those virtual channels have to correlate on the other side as well. So there's two types of decompositions that are happening there that's important for you to understand.